so this paper sort of brings in, I think, some insights from philosophy to the economic growth literature. So in particular, as you all know better than me, philosophers have carefully considered the difference between making people happy on the one hand versus making happy people on the other hand, and studied the pros and cons and really given that careful consideration. Not so for growth economists. We focused exclusively on making people happy. And in some sense, this paper says, well, what if you take a more balanced approach and consider both? So it basically brings a total utilitarian perspective to evaluate the outcomes of economic growth. And it's joint with a graduate student, Mohammed, Mark, and Pete. Okay, so as I just mentioned, economic growth is almost always measured in per capita terms. And there are lots of great reasons for that. I've spent my life doing that. I think that's really valuable in many, many ways. The idea in this paper is, well, let's at least consider the possibility that putting zero weight on having more people might not be the only thing we want to do. Okay, so I see this paper as not advocating we should all switch over and do things a different way, but at least let's look at an alternative and see if it says something very different or says something pretty similar. So putting zero weight on people just, is definitely extreme. So one way to motivate this that I like is to consider the following hypothetical. Suppose we have two countries, two economies, and they both have exactly the same production opportunities. Okay. One chooses to use its output to have constant population and put all the resources into raising per capita consumption. And the other does the opposite. It holds constant per capita consumption and invests all its resources in adding more people. Okay. Well, to a growth economist, we look at the first one and say this is a growth miracle, and we look at the second one and say this is a growth disaster. But I kind of began the example by telling you they had exactly the same production opportunities, so it's weird to label them so differently. Okay. Now this is not just a hypothetical example. In fact, Japan and Mexico are not too far from this. So Japan today is 6 times richer on a per capita basis than it was in 1960, while Mexico is only 3 times richer. But Mexico's population is 3 times larger than it was in 1960, whereas Japan's is only 30% larger. Okay, so we typically say Japan is the growth miracle and Mexico is below average, but are we so sure? What about 30% people? That's just so little. So the question here is, take a total utilitarian perspective. How much has population growth contributed to some notion of aggregate welfare growth? And I'll be careful about what I mean by that. Obviously, this total utilitarian perspective is useful for lots of other questions, and economists have used it in some of these other cases. So evaluating the Black Death or HIV and AIDS, Alan Young has a nice paper, or COVID-19, or China's one-child policy. That's closer because it's not just deaths, it's the missing births in some sense. Or an example I like is population growth over thousands of years, right? So as you know, for thousands and thousands of years, there was no growth in per capita income. And then the last 200 years, you get the vertical part of the hockey stick. But that's not to say there was no technological change over those thousands of years. We invented, fire, the wheel, agriculture, steel, bronze, et cetera, et cetera, et cetera. It's just that all of that innovation showed up on the extensive margin. It showed up by adding more people. And so why should we call that zero growth? Okay, I'll come back to that example in an empirical application. Another final example, what fraction of GDP should we spend today to mitigate climate change in the year 2100? Surely that depends on how many people are around in 2100. If there are only 1 billion people in 2100, we might spend less. If there are 10 billion, we might spend more. So the number of people, it's pretty clear it matters, and you shouldn't just ignore the number of people for many applications. Okay, so the outline for the paper, there's a really simple baseline calculation. I'll show you that, I'll apply it. I'll show you robustness and how it changes if you change the assumptions. And then part 3 kind of has a sort of a richer micro model. I'll probably stop before part 3 and just take questions, because I think it's a lot more fun if I hear from you. But maybe I'm not used to giving talks where no one asks questions, so maybe I'm gonna have plenty of time. Who knows? Okay, so the baseline first, and then the robustness. All right, so the setup here is, suppose CT is consumption per person. U of CT is the flow utility enjoyed by each person. And they're n identical people, no heterogeneity at all to start. That's the simple model. Robustness will add heterogeneity. Summing over these people, the aggregate flow of utility is just n times U of C. Okay, and so a couple of comments on that. First, this use of the word flow. This is not lifetime utility. I'd love to do it with lifetime utility, but there are a couple of reasons not to. First of all, I don't know what the future holds. So what is my lifetime utility? I don't know. So that would be awkward. Second, the macroeconomic outcomes that growth economists look at, like GDP per person, that's a flow concept. So this welfare flow is going to parallel the flow that is GDP. So that's nice. Couple of other comments. You'll notice if you exist, you get U of C. If you don't exist, you get 0. The 0 is a free normalization. You can make the 0, 200 or negative 37 million or a billion, and that everything's robust to that. As many of you know, and if I let you ask questions now, you would wave your hand if I didn't have this, and you might even wave your hand anyway. I'm making an implicit assumption that is important. Non-existence is the same whether it's non-existence pre-birth or non-existence post-death. Okay, 100 years before I was born, there's some utility flow, maybe, I don't know, maybe that's just 0 by definition. 100 years after I've turned to dust, in both of those states, I don't exist. I'm calling them the same. This is an assumption, and you might not want to make that assumption. It's not clear how to depart from it. This is a benchmark, n times U of C, very natural. So we like this as a benchmark, but it absolutely is making assumptions that it'd be great to be able to relax, but I think it's pretty hard to relax in practice. Okay, but that's our baseline case. A slide I probably don't need here about total utilitarianism. I should thank Gustav and Tom for helping me understand the axiomatic justification. I cited economist papers. I'm sure I should have cited some philosophy papers instead. You know that stuff better. I'll leave that out. Maybe I'll go to this last point, because this one is important to appreciate. The people we're evaluating here are not hypothetical people. These are people who exist. They didn't exist maybe in 1960, and they exist today. And so there's no sort of it's not a hypothetical people. All these people exist, and they each get some utility U of C, and we're going to value them according to their utility. So that's kind of what's going on here. All right, so this is a paper about growth rates instead of levels for reasons that we could talk about. So I'm going to take this equation and take the log derivatives of it and then put it in consumption equivalent units. And I'll talk about what that means. So the first equation is the log derivative. The second equation gives me the consumption equivalent units. So let me just talk about that equation instead of going through the second line. So consumption equivalent welfare growth is the sum of per capita consumption growth, that's the last term, plus population growth, where population growth has a coefficient V of C on it. What is that coefficient? Well, so first notice if there's 0 population growth, consumption equivalent welfare growth is just per capita consumption growth. That's the sense in which it's in consumption units, for example. The coefficient on population growth, notice the numerator is just U of C. We value people the same way they value living. They get U of C utils, so every time we add some people, we value them at the U of C. To get it in consumption units, we divide by the marginal utility of consumption, right? That converts utils into dollars, right? And then because we're in growth rate space, we take the ratio to per capita consumption. So that's what that V of C, it's the value them at the utils, convert to consumption units, growth rates take the ratio. So that's V of C. V of C has a nice interpretation, and you'll see more when I calibrate it. It's the value of having one more person live for one more year, measured as a ratio to per capita consumption, measured in years of per capita consumption. So I'll talk more about that in a second. But what you can see very clearly here is 1 percentage point of population growth is worth V of C percentage points of consumption growth. And everything's about how do you measure V of C? Okay, and then we see consumption growth, we see population growth, multiply by the V of C, and look at a lot of countries. That's all the paper is. So measuring this V of C is very important here. And Unfortunately, in economics, through the, liability system, largely when, if unfortunately I get run over by an electric skateboard and that kills me, my family sues somebody and they have to figure out how much damage is. And there's a lot of that stuff going on to figure out damages. And that's where these value of life numbers, why so many people study them. The Environmental Protection Agency, the Department of Transportation, they use value of life numbers when they're deciding, how much do we bank this highway? How much do we reduce pollution with pollution scrubbers or whatever? How do we bank? So there are numbers out there. The EPA's number, for example, is $7.4 million in 2006 for the average American in some sense, okay? So to compute V of C, we need to take that 7.4 million, that's for a lifetime. Well, for the average American, let's say is 40 years old, so they might have 40 more years to live. So 7.4 million divided by 40 is 185,000. So $185,000 per life year. And that's a very conventional number, the kind of numbers that health economists, David Cutler, use all the time. So that's a conventional number. And then per capita consumption in the US, $38,000. So the ratio of the value of a year of life to per capita consumption is 4.87 in the US in 2006. Okay, so what's interesting about that number already is going back to this equation. I said I'm going to take consumption growth plus population growth times V. If V were some number like 0.1 or 0.2, population growth is just not going to matter. What I've just told you is V in the US in 2006 is a number like 5. Okay, so that's already, the rest of the paper is just, it's that, that number is huge. And so population growth is going to matter a ton because the EPA, the Department of Transportation, all of us act as if lives are incredibly valuable. Okay, and by the way, this value of life, you may know already, where do they get these numbers from? They get it from labor market studies where, I can decide to be a janitor or a construction worker. Being a janitor is really safe. Being a construction worker is pretty dangerous. How much additional do I need to be paid to take that extra risk to my life? Use that wage differential relative to the probability of dying to back out a value of life. So these are from real economic decisions that people make. It's not just survey people to ask how valuable is your life. Okay. Okay. 5 for the US in 2006. What about the US in other years? What about other countries and other countries in other years, right? So we need a lot of these numbers to do the empirical application. Here, unfortunately, the studies in the US, to be honest, aren't great. You can identify problems with them. The studies in other places aren't great. So what we're going to do, and we can talk about how this matches up with the other studies. I think it matches up reasonably well, is instead of gathering 10 other studies and interpolating, a natural thing to do is assume a utility function and use the utility function to extrapolate. Okay, and there are pros and cons to this. We think we kind of know something about the shape of utility functions around where we've looked, but do we know what the shape of the utility function is far away from the US and the UK? That's a problem. But bear with me for a second. Assume log utility, the simplest way to start. U of C is U bar plus the log of C. V of C, take the U of C, divide by U prime times C. U prime C times C is just 1. So interestingly, and I didn't realize this until recently, what are the units of log utility? Well, they have an interpretation that U of C is V of C for log utility. So it has the interpretation of the value of a year of life relative to per capita consumption. Okay, notice next that V of C for log utility is an increasing function of C. The richer you get, life becomes increasingly valuable. That seems reasonable, but it's in a stronger sense here, which is life becomes increasingly valuable even relative to per capita consumption. Okay, so there's a strong income effect here. That's just what the utility function says, so we're going to go with it. We'll relax the utility function to constant relative risk aversion with different parameters later. I'll calibrate. So we could choose consumption units. We could measure consumption in dollars, thousands of dollars, billions of dollars, pounds, euros, whatever. We're going to normalize units of consumption so that consumption in the US in 2006 is 1. Since the log of 1 is 0, V of C equals 4.87 for the US in 2006 implies the U bar is 4.87. So that gives me the one parameter that I needed to know of the utility function. One observation on the value of life gives me the U bar. That was my one parameter. Now I can extrapolate over time and across countries. Okay. If we extrapolate over time, notice V of C is the log of C. Consumption rises exponentially, so the log of consumption rises linearly. That's what you see in the data, right? So there's the 5 up there. The interesting question is, how quickly does it decline as we go back in time? And the answer is, if you go back 200 years, the value of life in the US is some number like 2. Okay? So not only is the number large today, but it was pretty large even 200 years ago. So some number between 2 and 5 for the US in the last 200 years is that what you should think about that coefficient on population growth. Hey, what about across countries? Take the Penn World tables, read off the data on consumption, plug that in, and then the value of life in 2019. So Germany and Japan are pretty close to the US, Mexico, Brazil, South Africa in between. Ethiopia, one of the poorest countries in the world, is around 2. Okay. So now in 2019 across the world, we see 2 to 5. And in the US for the last 200 years, we see 2 to 5. Again, still pretty big numbers. So this population is going to matter over time and across countries. Okay, let me skip that slide. So just to recap where we are before I start plugging in numbers, you can see it's a really simple exercise. The growth rate of consumption equivalent welfare, where you value population growth in consumption units, so everything is in consumption units rather than utils. Utils wouldn't make sense here, right? The growth rate of consumption equivalent welfare is per capita consumption growth, the thing we always look at, plus population growth multiplied by this coefficient V of C. V of C values lives the way people themselves seem to value lives in making economic decisions. Okay, so that's the price of people is this V of C. Notice, now you can see from this perspective, V of C equals 0 is just completely extreme. People value their lives an incredible amount. Why would you want to ignore that when you're computing some growth measure? Notice, by the way, V of C equals 1 would say consumption equivalent welfare growth is just aggregate consumption growth. You might have thought, well, if you want to value the population growth, just use aggregate growth. That would be one way of doing it. Even that, though, is somewhat extreme relative to the 2 to 5 that we see in the data. And so on average across countries in 2019, the number is something like 3. In the rich countries, it's something like 5. So we're going to be a long way from using aggregate consumption growth to value things. Okay, so if we look at 100 countries from 1960 to 2019, computing the annual growth rates and then averaging everywhere, changing the value of life as we move forward in time, what do you get? So in the middle, you can see per capita consumption growth is about 2%. That's a standard number, fine. The population term, V of C times GN, is 4%. So consumption equivalent welfare growth on average across 100 countries is a number like 6%. So traditional number 2, new number 6, the population growth term is twice as important as the term we usually look at. And this is just exactly because the value of life is so high. The value of life is 2.7 averaged across these countries over time back to 1960. And so, ignoring population growth makes a huge difference. Okay? Not everywhere, there's heterogeneity, and so I'll come back to that. But so rather than show you these summary statistics, I think it's helpful to look at a few examples. Okay, so look at Mexico first. Per capita consumption growth is below average, 1.8%. Population growth is 2% per year. But Mexico's a middle-income country. Its V is pretty high, 3.4. 3.4 times 2.1, 6.8, plus the 1.8 gives you 8.6. Mexico, that looks below average on a per capita basis, is one of the growth stars when it comes to aggregate growth, consumption growth, because they're adding people and they're pretty rich, so the people are worth a lot. Okay, jump down to the United States, 2% consumption growth, 1% population growth, but the US is pretty rich, so the V is a number like 4, average since 1960. So you add 4% to the 2 and you get 6.5. So the US kind of looks like the average country in the world from this perspective. Look at China now. China, one of the fastest growing countries in the world. On this table, fastest per capita consumption growth. One-child policy means lower population growth, but still 1.3 since 1960. But China's poor enough that the value of life, when you take the log of consumption for China, the value of life is only 1.8. Right? So population growth only adds about 2 percentage points to China's 3.8. So China's below average in this consumption equivalent growth. The fastest growing, one of the fastest growing countries in the world, jumps way down below average, below the United States. Okay, how about Ethiopia? 2.5% per capita consumption growth, 2.7% population growth, the fastest population growth in this table. But Ethiopia is very, very poor. The VFC extrapolated this way is slightly less than 1. And so all that population growth doesn't add very much. And so Ethiopia is still well below average. Okay? By the way, you might look at this and say, wow, are we really sure we should value Ethiopians different from the way we value people in the United States? Well, you know, that's a philosophical kind of question. You've thought about it probably more than I have. We'll do it another way later on in the robustness check. But the economics wants you to do this. Okay. And then finally, Japan versus Germany, right? Japan and Germany have some of the slowest population growth rates in the world. Japan, 0.5% per year. Germany, 0.2. I was really surprised by this. I hadn't appreciated that. Some of the fastest per capita consumption growth rates in the world. These are some of the growth stars in the post-1960 period. But even though they're rich, so the V is high, population growth contributes very little. And so Germany is below Ethiopia, Japan just slightly above Ethiopia. So the impression I want you to get from this, making this adjustment completely changes how you evaluate the growth rate outcomes of different countries. So it matters a lot, right? Here's the same table graphically. I'm going to show you some other graphs that both the table and the graphs are useful. So the way to read the graphs, the blue numbers are the per capita consumption numbers. The green numbers are the V of C times population growth numbers. And the number at the top of the bar is the total. Right, so what you should do here is just how big is the green bar relative to the blue bar? That's the importance of population growth in those countries. And you can see for a lot of countries, population growth is incredibly important. And for Japan, Ethiopia, and Germany, population growth is much less important. Okay. Here's another chart I like. It takes a second to describe, but I think it's worth it. So where are countries in the growth rate distribution? Okay, the blue bars are where are the countries in the per capita consumption growth distribution, our traditional measure of growth. The brown bars are where are countries in the consumption equivalent welfare included population distribution. Okay, so Mexico, South Africa, Kenya, some of this, they're below average, right? 30th percentile for South Africa in terms of the blue bars. Per capita consumption growth, these are growth laggards. Mexico's below average. Germany, Japan, and China, growth stars, you know, up 75th, 80th, 90th percentile. If you look at the brown bars, though, the mirror image, it flips around, right? It's remarkable, and there's nothing, there's no reason why it would be the mirror, but you know, it's just for these countries that happen to be true, right? Mexico, 90th percentile, South Africa, 80th, Kenya, you know, nearly the 70th. Germany, the 10th percentile, Japan, the 30th percentile, China below the median, right? So again, these adjustments make a big difference. Okay, yeah, we can make lots of these graphs. So I'll just show you a few. Here's by continent. So you can see a lot of continents, the green bars are incredibly important, except for kind of Europe and parts of Asia. If you're curious about what do all the 100 countries look like, here's a graph: consumption growth on the horizontal axis, the consumption equivalent welfare growth on the vertical axis. One thing I found interesting, there are a bunch of countries that have negative growth in per capita consumption for 60 years. You know, that's just a tragedy. There are no countries that have consumption equivalent welfare growth below 2% over the same period. Right? The poor countries have fast population growth, and that helps out. You can see the really high numbers, right? So Jordan or Singapore or Hong Kong, you might start to worry about migration. One of our robustest checks corrects migration, so that's coming. But yeah, there's some really rapidly growing countries. And remember the rule of 70, you know, growing at 10% per year, you're doubling every 7 years, right? So these differences matter. You'll see a version of that statement in a second. Finally, we could do it over decade by decade. Here's Japan by decade. You could see that growth miracles were even more miraculous in the 60s and 70s when you add the green bars. And you could see the recent decade is even worse than per capita consumption growth makes it appear, because population growth is negative in Japan. Negative population growth, when life is valuable, is a deduction. And so, in fact, consumption equivalent welfare growth in Japan for the last decade is negative. Okay, so an incredible change relative to the 10% growth in the 1960s. Yeah. Oh, thank you. Yeah. We're good. Here's China. An important thing, I was surprised by this. The one-child policy, not quite what you see. You know, V of C is going up as China gets richer, even as population growth is coming down. So the V of C times population growth tends not to shrink as much as you might have thought. Sub-Saharan Africa, the decades that are just disasters from the 70s to 2000. If you count the happy people, it gives you a different perspective. Finally, this one I like a lot. This goes back to the growth over the long term. 500 years of per capita consumption growth at the world level. Turns out per capita consumption growth over these 500 years averages 0.5% per year. You accumulate that over 500 years, it's a factor of 20. Okay, let me skip the green line, the aggregate consumption growth, go directly to the consumption equivalent welfare. Consumption equivalent welfare growth is 1 percentage point faster. Right? But you know the power of compounding, 1 percentage point faster for 500 years, factor of 3,714. Right? So just, you know, are we 20 times better off than we were 500 years ago, or 3,700 times better? It makes an enormous difference. Okay, I do need to say this. What we're not doing, we're studying the marginal benefit of people along a social welfare function. We said nothing about production functions. So you might be interested in lots of other questions like what's optimal population, optimal fertility, what's the demographic transition, good or bad? You have to specify the production side of the model to answer those questions. Those are interesting questions. Maya and Pete and I are working on that now, but nothing in here. So in particular, this paper doesn't say, it can't say that people in Japan are having too few kids. Right? We're only looking at the benefits, not the costs. And so who knows? Well, you know, next year, if you invite me back, maybe, or Maya can present, maybe we'll have an answer to that question. Okay, robustness. What we do in the robustness checks, you know, double or cut in half the value. Actually, it's 50% more or half the value of life, different utility functions, different gammas, constant relative risk conversion. Add in inequality, relax the representative agent assumption. How much is mortality versus fertility? Adjust for migration. The clock stop? Oh, 22. And we go till 5:40. Is 5:50. So I have a lot of time. Okay. Oh, I see. Okay. So the 20. Yeah. You clarified for me before, and I just did this calculation. Okay. Good. I can. See, I told you I'm almost done. I can go more slowly. So robustness to different values of life. You know, we're going to cut it in half or increase it by 50%. So that'll imply a value of life of 3.7 million versus 11 million. The Department of Transportation, for example, looks at 9 studies they think are really good and says 4 to 10 million in 2001. If you put our numbers in 2001 dollars, we're looking at a range of 2.8 to 8.6. So kind of on the low side relative to that. There's a big range. It's hard to know, but I'll show you what the outcomes look like. Here's a plot of V of C for different utility functions. So I should have put the utility function up here. It's C to the 1 minus gamma over 1 minus gamma. So constant relative risk aversion, gamma is the risk aversion. What if you, so the log, the blue line is, V of C looks like log of C. That's what you're seeing there. What if gamma is 2? What if gamma is a different number? So you can see as margin utility falls more quickly, the value of life rises faster. What's going on here is, once you're you and me, we have a great life. Oxford's great, Palo Alto's great. We have a good life. Margin utility is really low. I don't need another iPhone or another TV. I need more years of life to enjoy this high living standard. That's kind of what's going on here. And if margin utility falls even faster, then the value of life rises even faster with consumption. So that's the gamma equals 2. Notice gamma, you could find a gamma, in this case 0.794, such that the value of life would be constant. And this is all changing the U bar as you change the gamma, because you have to recalibrate to the value of life. That's what everything being 5 at 1. And then you can even have the value of life decline. As gamma is a half, the value of life declines. So what I like about this picture is it tells you no matter what gamma you choose, population growth is important either historically or in the future, or both. Right? If you thought gamma was a half, you're going to say, wow, my numbers underestimate how important population growth is. If you thought gamma was 2, my numbers maybe overstate. I'll show you the numbers in a second. But the future, it's going to be even more important than we thought. Okay, so you're not going to, changing gamma doesn't get you around this stuff being important once you calibrate to a value of life. Okay, so there are a lot of numbers here. The way to read it, these are a bunch of robustness checks. And going across, we show you the average across the 100 countries, and then a selection of countries just to help illustrate what's going on. I put per capita consumption growth in the first row, just so you'll see what are we comparing to. So second row is the baseline that I showed you, very different from per capita consumption as we've discussed. And then a bunch of different checks. So cut the value of life in half or double the value of life, 4.5 or 9.8. So you shouldn't believe that the 5.9 or the 6 is the right number. It is sensitive to what values you plug in, not surprisingly. If life is more valuable, it's even more important. But all of these numbers look very different from the first row. Okay? So I can't tell you what the right number is, but I can tell you it's not the first row, at least if you want to value people somehow. Gamma equals 2, you can see historically it's a little bit lower. That's the 4.6, but in the future it would be even more important. And then what if you want a constant value of life across consumption? You want to value the people in Ethiopia the same way you value people in the US. You can value them with a high value of life, that would be the row 7, an average world value of life, that would be row 8, or aggregate consumption, V equals 1. And again, you can see all of these numbers are very different from the 2.8. Ethiopia, if you value their lives the same way you value US lives, 15.4% because of all the rapid population growth. Okay, so yeah, I think you understand the nature of the robustness. It's not that our baseline is right, but no matter what we do, it's very different from per capita consumption. Okay, this one, moving beyond the representation, is nice. So we didn't do this at first, and then someone asked me a question. It was a really great question. He said, okay, think about Mexico. In most countries, it's the poor people who have high birth rates. And so maybe you're valuing the lives with the average consumption, but really all the births are among poorer people on average. And so you're overstating the value of life and overstating the role of population growth. That was an interesting question. It turns out, so, you can do it with, add up across the U of C's where there's heterogeneity, go back to log utility again, and let consumption be log normally distributed so we can get a bunch of standard deviations from around the world and make the calculation pretty easy. So what happens? So you get a formula. The V of C is the same V of C we had before. It's based on average consumption. And then you want to make an adjustment for how much inequality is that reduces the V of C. Okay, so it goes in exactly that direction. Okay, So, and then there's a rising inequality would be a deduction too, but that's, yeah, so that's going to be in there. So we have numbers for, I guess we didn't say how many countries here. I don't remember, a bunch of countries, probably not all of them. Interestingly, it doesn't make that much difference, right? So look at Mexico. Mexico, it's a 1/10 of a percentage point. Okay, that's surprisingly small. Why is it small? Well, in fact, as I described the experiment to you, I was neglecting one thing that ex post turns out to be important, which is if all the births in Mexico are to poor people, that's going to reduce the level of per capita consumption in the future, right? That was already in our baseline result. So the direct effect is going to show up in the reduction of per capita consumption, and the inequality adjustment on top of that turns out to be pretty small. Okay, so this was good because I thought this was a great point. This could have mattered, and it was interesting to realize, okay, it's not a big deal. What about births versus deaths? I think what I'll tell you here is, on average, about 3/4 of the population growth is due to fertility, and 1/4 is due to mortality. Pete and I, in an earlier paper, said rising life expectancy added about a percentage point. For the world, we're getting population adding 4, and so you can see the 1/4 is sort of there. So, you know, fertility and mortality are both important here, but fertility is maybe 3 times more important in these data. Adjusting for migration. So yeah, when you see, thank you, when you see Mexico and Israel and Hong Kong, you realize, well, there are a lot of people leaving Mexico and coming to the US. Who gets credit for those migrants? It turns out the way our baseline works is we count people based on where they're living today, so, you know, where they're living when we see the GDP. And so our baseline calculation gives the US all the credit for the people who moved from Mexico. Okay? I don't know what the right thing to do is, but we could do the opposite. We could say, let's give all the credit for the migrants from Mexico to the US. Let's give the credit to Mexico. Okay? And we can see what difference that makes. And presumably the truth is somewhere in between. And when you do that, okay, so blue bars are the baseline, brown bars are the migration adjustments. And you can see, like, these are some of the countries where it matters most. So in the US, it knocks off a percentage point. In Hong Kong, it knocks off 2 percentage points. In Australia, maybe a percentage point and a half. Ireland adds a percentage point, Mexico a percentage point, Philippines half a percentage point. So it does matter, but it doesn't change the picture. And I think, yeah, I took off the graph where we showed, oops, sorry, where I showed the 45-degree line with the 2 things. You know, other than a few countries, they're really concentrated on the 45-degree line. So this doesn't matter. So when I look at the relaxing our baseline assumptions, definitely the value of life is going to matter a lot. The gammas, you saw which way it goes. So let me just, coming to the end, let me summarize what we do here. Maybe I'll show you the slide. So one way you know how our baseline model is wrong is people have kids because they love them. And yet in our baseline model, if flow utility is just U of C, why would I ever have any kids? So it's kind of, it's missing things that are important. And so this last part of the paper just does a more careful calculation where you recognize that, you know, having kids gives parents utility, that fertility rates are falling. Juan Carlos Cordoba has a paper where he just does that part. He does the he does the little n, not the big N in some sense, and then differences it. So lower fertility actually lowers growth in his calculation. On the other hand, falling fertility, there's a reason why people are lowering their fertility. It's because they're investing in the quality of their kids, the quality-quantity trade-off. So you do want to value the extra human capital we're giving to the kids and the consumption that implies. And so we kind of write down a richer model with time use, fertility, consumption. We can only do it for a few countries because we need the time use data on how many kids are people having, how much time are they investing in their kids. And so I think we have, let me not show you the structure in detail. Yeah, the US, Netherlands, Japan, South Korea, Mexico, South Africa. So a range of countries. The periods are not exactly the same periods we've looked at. What do we get? So the macro calculation is the baseline redone for the relevant years, so it's comparable. And the micro is the rich calculation with all these additional terms. And you can see, it matters a little bit, but not a ton. And basically the quality quantity terms, fewer kids is a negative, better educated kids is a positive. Those kind of offset. And yeah, it's worth doing, but it doesn't change the picture, especially if you look at what share of growth is due to population. These are very high, and this shows you robustness to different parameters, different values of life. Okay, so that's it. So what do I take away from this? Again, there are lots of important things we learned from per capita outcomes. We're not claiming you want to switch over and only do this from now on. But unlike the philosophers, us economists have been obsessed with per capita outcomes and completely ignored adding people. And maybe we need to have the same debate that you guys have had so that we fully understand the pros and cons of these different perspectives. Because what we found out here is it makes a big difference. It's not something you can just ignore because it's small. It's something that absolutely matters. And the reason it matters, again, it's just that the value of lives are high. The $10 million value of life that we use in the US today says adding a new person adds $10 million to the economy. Again, subject to some philosophical debates that you'll raise now. So anyway, I hope people continue to work on this and at least explore the alternatives. So I think it should be important. Okay, thank you.